In the previous video, I showed you how to get electric potential from electric field for conductors, for a spherical conductor and a cylindrical conductor. In this video, I'd like to talk about how to do the same thing for insulators. So let's just have a spherical ball that's charged throughout its volume. And the charge density I have picked for this is rho of r equals a over r. Now if you examine that expression, it's not valid as r goes to 0, but it turns out that it doesn't matter. The charge enclosed, even in a very small volume, turns out to not blow up, although the density seems to behave badly at the origin. So we won't worry too much about that. Now, the proper way to do this problem is to first find the electric field because it's endowed with spherical symmetry. So I would take two Gaussian surfaces. You would use as many Gaussian surfaces as you need. There's really only one Gaussian surface. Imagine this is a surface that starts from 0 and goes all the way out to infinity, and you're capturing it at 2 points using a camera. That's the reason why I never put different values of r for these Gaussian surfaces. I call them by the same symbol, r. I will call them different surfaces S1 and S2. Now, the left-hand side of Gauss's law goes as usual for spherical symmetry, but let me just run through that argument for the sake of old times. So this is E and dA. It's going to be E and dA on that side. So it looks like the area vector and the electric field are everywhere parallel. So the left-hand side of Gauss's law Gauss's law, first of all, is the following statement. It is the oriented closed double integral over any of the closed surfaces Si, where I goes from 1 and 2, E dot dA, and that's called the flux enclosed by the ith surface, the closed flux. That's also equal to the enclosed charge by the ith surface divided by epsilon naught. So that's the statement known as Gauss's law. How are we going to use this in our problem? The left-hand side, as I said, can be simplified quite readily. It just becomes Si E times dA times cosine of 0 degrees. And that E can be pulled outside because that's just the magnitude of E, which is constant throughout the Gaussian surface. It only depends on the Gaussian radius r. And then I have the double integral of the area dA. Now that, because I've called both of these Gaussian surfaces the same radius r, is just E of r times 4 pi r squared. The right-hand side then is what we need to worry about. The enclosed charge over epsilon naught is the right-hand side. Now, off to the side, I'm going to talk about the charge as a function of radius r. Now, if you go from 0 to r, how much charge is enclosed? That's given by the function integral 0 to r times rho of r times the spherical symmetry area element, which is 4 pi r squared dr. So if I substitute for rho here, I'm going to get the integral from 0 to r, and rho is going to be a over r times 4 pi r squared dr. Notice that one factor of r cancels out, and I can take 4 pi times a outside because it's constant, and I get 4 pi a integral 0 to r dr. And that integral is just r squared over 2, so I get 2 pi a r squared when I evaluate that integral. So the right-hand side of Gauss's law is just q of r divided by epsilon naught for r less than or equal to r, and it's Q at capital R divided by epsilon naught if R is bigger than or equal to R. Because at R equals capital R, the sphere ends and there's nothing beyond that. That's the reason we max it out at that point. So let's work out the electric field. I get the electric field E of R times 4 pi R squared is equal to, now that is Q of R is 2 pi A R squared. So I get 2 pi A R squared over epsilon naught for R less than or equal to R, and it's equal to 2 pi A capital R squared over epsilon naught for R bigger than or equal to R. The last step is to divide both sides by 4 pi R squared. So I'll get the electric field as a function of R written in vector form to be, now you notice that the R squareds cancel out and I just get 2 in the denominator. So this is going to be A over 2 epsilon naught R hat for R less than or equal to R. And here there's no cancellation, but the 4 pi's and the 2 pi cancels out, so I get A R squared over 2 epsilon naught little r squared for R bigger than or equal to R. Just as a quick check, let's make sure that these values agree at R equals R, as they have to. At R equals R, I'll have the numerator with capital R squared and the denominator with also capital R squared, so the R squareds cancel out and I get A over 2 epsilon naught, which is the same as that. So it does indeed agree at the boundary. Now that we have the electric field written out in vector form, we can perform the computation to find the electric potential difference. The master equation for potential difference is the change in potential is equal to the negative integral initial to final, the electric field dotted with the ds vector. Now this has to be evaluated in a piecewise fashion because there are two expressions for the electric field which are different from each other. As a first step, let's consider the structure of the path that we're going to be choosing. Because these are path integrals, in fact I forgot to put here any path. Now obviously you want to choose the path that you can actually work with, and usually in cases like this the simplest path is the radially outward path. So we're going to be using that. 0 or infinity. That's it. Now what we're going to do is the first calculation is going to be carried out from some interior point which I'll call R up to the boundary along this path which I'll call gamma 1. And the second integral will be carried out from some point R here all the way to infinity. And that'll be along a path called gamma 2. I'm making these notations, gamma 1 and gamma 2 coincide with the Gaussian surface notations S1 and S2. As a matter of fact, it's a better idea to do the second integral first because the potential at infinity is a known quantity. The potential at infinity is taken to be 0 by convention. So we can use this in order to simplify the problem. So let's start with the S2 Gaussian surface along path gamma 2 first. The change in potential energy is V at infinity minus V at this R value, whatever it is. And that's going to be minus the integral from R to infinity E dot ds. The electric field is pointing outward because it's in the R hat direction, and dr is also pointing outwards, so the angle between them is 0 degrees. So I'm going to get E times dr times cosine 0 degrees. And here I'm going to put this expression in. I'll pull out all the constant looking terms. So I'll get A over 2 epsilon naught R squared times the integral from R to infinity of dr over R squared. That integral is just negative 1 over R, which cancels this negative sign nicely. So I'm going to get AR squared over 2 epsilon naught times 1 over R evaluated between r and infinity. Now the upper limit gives me 0 and the lower limit gives me 1 over r, so the answer is negative ar squared over 2 epsilon naught. The negative sign comes from the fact that the lower limit is subtracted. On this side, I'm going to get 0, because that's what the potential at infinity is by convention, minus v of r equals negative ar squared, oops, I forgot this r here, over 2 epsilon naught r. So cancelling out the negative signs, I have the expression for the potential outside the sphere. Our next calculation will give us a potential inside the sphere as well. So that's for the Gaussian surface S1 with the path gamma 1. So that's v of r, the delta v is v of capital R minus v of little r, is equal to negative integral r to infinity, the same deal, e times dr times cosine 0 degrees. And let's find out what e is. E, I have to use that one this time. So it's a over 2 epsilon naught times dr. And that's all there is to do. So, no, that's not 0. This is r to capital R, not infinity. So this gives me negative a over 2 epsilon naught capital R minus little r. Now we have a slight problem, and that is we don't know what v of r is. But notice that just as we did matching of the electric fields at the boundary, we can also do matching of the potentials at the boundary. V of r, whatever it is, should also be the same thing that I get from this expression. So I'm going to substitute for this here. Now if I put v of capital R here, one of the factors of r's cancel out, and I end up getting ar divided by 2 epsilon naught minus v of r is equal to negative ar over 2 epsilon naught plus, because minus of a minus is plus, ar over 2 epsilon naught. Now I can get the potential inside by I'll move the v of r to that side, so it becomes positive, and I'll move everything here to the left. So ar over 2 epsilon naught comes with a negative sign. When it goes to the left, it becomes positive, and I get ar over 2 epsilon naught plus ar over 2 epsilon naught, which is just ar over epsilon naught. So let me write that first. And then when I move this one to the other side, it gets a negative sign. Now, just as a sanity check, it might be a good idea for you to check here as well that the two potentials agree at r equals capital R. At r equals capital R, I'm going to get ar over 2 epsilon naught from this. Here I'm going to get ar over epsilon naught minus ar over 2 epsilon naught, which is again ar over 2 epsilon naught, so they do agree. Let us plot finally, to make sense of this problem, both the electric field and the potential as a function of distance, and see the relationship between the two. There's a very important relationship between the electric field and the electric potential. What is it? If I plot the electric field as a function of distance, I'm going to observe the following behavior. The electric field is constant inside, and then it goes off as 1 over r squared subsequently. That's Gaussian surface S1, that's Gaussian surface S2. Now what happens when you do the potential? When you plot the potential, the potential goes off as 1 over r outside, so that is barely distinguishable from 1 over r squared. It's another decaying curve. But inside is what concerns me. Inside, it's got some maximum value at r equal to 0, which is ar over epsilon naught. And it steadily decreases to half that value by a straight line. and subsequently it falls off as 1 over r, as I mentioned. So it's a linear decay, and you can, I think it's a good idea to label the trends here. That's constant, and that's a linear decay. That's 1 over r squared decay, and that's 1 over r decay. Now the relationship between a potential and electric field is that the negative derivative of the potential is the electric field. So negative dV by dr must be equal to the electric field. And let's just check that as a final sanity check. The derivative of this would be a negative quantity and constant because it's a constant negative slope. Well, the negative derivative of that would be a positive constant, so that's good. The derivative of 1 over r is negative 1 over r squared. Well, the negative derivative of 1 over r is 1 over r squared, so that's good too.